Right, so far in the course we've learned about matrices and how to go from linear system and translate it into a matrix and solve that linear system in a matrix. We've learned about vectors and how they look physically. And then in the last section we talked about adding and subtracting vectors and multiplying vectors with scalars. We're taking it a step further now. We're going to talk about the matrix equation, ax equals b. And this particular equation, ax equals b, is really, really important because it's one of the most pervasive equations or representations in all of mathematics and science in general. And so when we look at the equation ax equals b, it's a little easier to see in this form. We see that the x and the b are bold here. And so as a reminder, since the x and the b are both bold, that means they're vectors. In this case, they're column vectors. And then the matrix A, since it's a capital letter, anytime we see a capital letter, that usually means it's a matrix. Okay, so it's a matrix equation because we're multiplying a matrix times a vector, and we end up getting a vector. And like this sentence says, that equation is a really, really common expression in lots of math and science classes because lots of different applications are often posed in this form. And we'll see some in our course as well. Now, as I just said, in the last section we learned about messing around with vectors, adding and subtracting them, scalar multiplication, but now we're talking about multiplying vectors with matrices, okay? And so let's look at this definition here. So we've got an m by n matrix. Let's remind ourselves that that means it has m rows and n columns. And let's pull out the columns and let them be a1 through an, right? So capital A is a matrix, and then when we do lowercase a that are bold, these are the columns of that matrix. As you can see, this is A right here, right? And then X is in Rn, right? So let's dissect that. Rn, as a reminder, means real numbers with n entries, and so we're thinking about X as being a column vector that has n entries in it. Okay, could be X R2 in case there'd be 2 entries, R3 would have 3 entries, right? R10 would have 10 entries. Then the product of A and X, when we multiply A and X, is a linear combination of the columns of A using the entries in X as weights. In other words, and so these are all vocab words that we've seen in the last sections, right? And so you might want to go back and think about what linear combination means, for example. But anyway, it's written out right here, right? So A times X, matrix times a vector, can be written like this. So here's the matrix A, here's the column vector X. Right, so each one of these A's, A sub I is a column vector. And then we can see each one of these X's, X sub I, each one of those individual entries is a scalar. Right, so it's just a constant. And so when we do a matrix times a vector, we end up doing a bunch of column vectors scaled by these scalars, right? And so here's what that looks like in the next step, right? So the matrix, the column the column 1 in that matrix multiplies x1, right? Column 2 multiplies x2. Column 3 would multiply x3. And then the last column multiplies the last scalar. And so if we think about just like what one of these entries looks like, this is a scalar times a column vector, which is what we looked at in the last section, right? So this would look like x2, which is a scalar, and it's multiplied by a2, which is a column vector. It's the second column in the matrix. Okay. I'm just realizing since it's a column, these numbers should be switched. So first row, second column. Second row, second column. Nth row, second column. All right, so that would mean the second column of the matrix. Okay. And so you can see exactly what's happening here. We're scaling each column by the scalars in vector x, and then we're adding those things together, right? And so we're adding together a bunch of vectors that are all the same size, and so we'll get a vector out of that. Now, notice, in order for this to work, right, we have n columns in A, and there's n entries in the vector x, right? In other words, those two n's have to be the same numbers. And so in order for this to work in the first place, which is a very key thing in matrix multiplication, the number of columns of A has to match the number of entries in X. Okay, so the number of columns in the matrix has to equal the number of entries in the vector so that we can pair them up like this is being paired and add them together. And so let's relate this back to the last section. So last section we were doing scalar multiples of vectors and then adding them together. And so let's remind ourselves some of that language. So for example, let's consider these two vectors. U is 5, 2, and V is minus 3, 4. In the last section, we learned about linear combinations. And so a linear combination of vectors U and V could be something like 3 times U plus 7 times V. Right? We're doing scalar multiplication of the vectors, and then we're adding them together. That's a linear combination. That's what we learned about last section. And so that would look like 3 times this vector, 5, 2, plus 7 times this vector, minus 3, 4. And as we learned out in the last section, each one of these entries gets multiplied by 3, each one of these entries gets multiplied by 7, and then we add them together, right? And so this ends up being 15, 6, plus minus 21, 28. And then we just add the corresponding entries to get our final answer of minus 6, 34. But I'd really like to focus in on sort of this part of the expression, because notice that we're just doing a linear combination of some column vectors here, which looks a lot like this expression right here, right? And so let's rephrase this thing that we sort of looked at in the last section as matrix multiplication. Okay, so another way to think about this, in other words, 3 and 7 could be entries in a column vector X, right? And U and V could be the columns of a matrix. And so let's rephrase that in sort of that light and bring it into this section here. So we can think of this. We can think of the equation above as the vectors U and V being columns of a matrix. And so let's just call it A to make it look more like the definition. So A might have the columns U and V. Right, so I'm doing column vectors of A just like these have column vectors up here. And so that would look like this. Right, so now I've got U and V in a column as columns in a matrix. And then we could think about that as multiplying by the vector X that has those weights. In other words, let's rewrite this expression as this matrix times this vector would end up being that expression. Right? So in other words, i.e., A times X in this case with that A and that X would be this. I'm just sort of relabeling A and X as having columns A1 and A2, and those are columns that we just took as V and U. And if we have this multiplication, the 3 becomes the weight for the first column, and the 7 becomes the weight for the second column. And so we get this exact same expression that we just got. 3 times 5, 2. 7 times minus 3, 4. Right, and we'd get minus 6, 34. And so when we talk about AX equaling B, let me just slide back up to the top here. The matrix equation AX equals B, we've talked about AX so far. B is what you get when you multiply A times X, right? So in this particular case, we multiplied A times X. This is how we did it. And then this is the answer. And so this is the B in the above equation. Okay. Just to kind of drive that home, I want to write out the whole matrix equation AX equals B. So AX equals B became 5 minus 3, 2, 4. That's the A. X was 3, 7. And it equaled, after we did all that, minus 6, 34. And so we multiplied a matrix, right, a 2 by 2 matrix. It's 2 by 2. A 2 by 1 column vector X. And then we ended up with a equals a 2 by 1 column vector B. And so notice that these, we're going to come back to the dimensions in a second. So I'm going to write something in this space in a minute after we learn a little bit more. But here's what we did. We multiplied A times X. We'd use these weights. And then we ended up with this. And so that's our B. Thinking back to some vocab, because you'll see some of these vocab words in homework and stuff. This is called a matrix equation, right? It's a matrix equation, AX equals B. So we would refer to this as a matrix equation. It's a matrix equation because we're multiplying a matrix and a vector, and we get a vector, right? That's what makes it a matrix equation. Now, this expression up here, we're adding together, we're doing a linear combination of two vectors, and so that would be called a vector expression or equation. Okay, so when we have an expression that has vectors in it, it's a vector equation or expression. If you have an equation with a matrix in it, it's a matrix equation. And you'll see that in the notes sometimes, like, oh, what is the matrix equation associated with this? Or write your answer as a vector equation. You just want to be able to understand what the difference between those two things are. Okay, cool. Again, we'll come back to this in a second, and we'll talk about how the dimensions play a role in the solution before you even do anything. But let's learn a little bit more before we get there. Okay. So on the last page, we had two expressions, right? I just mentioned them. We had the vector equation, and then we had the matrix equation, and they're saying the same thing, right? They're doing the same thing. You get the sort of the same answer in both cases. And so it's important to realize that both forms of this equation, both forms of the previous example, convey the same information. You can think of the 3 and the 7 in that equation, right? The 3 and 7 in the equation 3u plus 7v as the weights. And in the vector equation, the weights are written as the vector 3, 7. Right? And so we had A was the columns u and v, our x was 3, 7, and then when you get an answer, that became the right-hand side of the equation, and that became our B. And so this is just summarizing what we just wrote out on the last page, right? The vector version of that equation looks like this because we're adding linear combinations of vectors, and then the exact same thing could be rephrased as a matrix equation, which would look like this. So just kind of summarizing what we just said again. And then this thing right here, AX equals B, this should really be a vector here. This is what we would call the general form of a matrix equation. And again, if you continue on with mathematics or science in general, things like engineering or chemistry and lots of things, AX equals B usually shows up further down the line. Okay. So I'm just going to do a couple more examples here, and then you'll have an opportunity to try a few on the next page. So I'm just going to show you a couple that have different dimensions here. And so in this particular one, we've got a matrix A here. It's a 2 rows by 3 columns. And we've got vector X, which is a 3 by 1. And so matrix A has 3 columns, A2, A3. Right, so you've got those 3 columns. X has 3 entries, and so we're able to do the multiplication. And let's determine the B in the equation, AX equals B. In other words, we'll multiply A times X. So we're going to do exactly what we did in the last page, just with a different sized matrix and vector. Right? So A times X would be these 3 columns, which I've labeled here, times the vector x1, x2, x3, which are these 3 right here. And we know based on the formula on the last page the first column gets the weight in the first vector, right? The second column gets the weight in the second entry, etc. And so this ends up being, I'm going to write all the details here, a1 x1 plus a2 x2 plus a3 x3. And we just start filling in these things, right? A1 is the first column here, and so that would be 8, 5. X1 is the first entry. It's just the number 1. We just keep doing it, right? So A2 is 3, 1. X2 is negative 1. A3 is minus 4, 2. X3 is 2. And so now we've got it written out as a vector expression, right? This is our vector equation, if you will. We scale each one of those vectors by the constant and add them together. Really easy, right? So 8, 5 times 1 stays the same. 3, 1 times negative 1 just makes them negative. 4, 2 times 2 becomes minus 8, 4. Add those three things together, right? You just add the corresponding entry. 8 minus 3 minus 8 is negative 3. 5 minus 1 is 4, plus 4 is 8. And so that's the b in the equation, ax equals b. Right. You take the columns of A, you use these scalars as weights, add them together. That's how you get ax equals b. Let me just do one more, and I'd like you to think about what happened here with the dimensions, right? So we multiplied just look at the equation ax equals b here. See if you can come up with a pattern. In this particular problem, a was a 2 by 3, x was a 3 by 1, and then we ended up with b, which was a 2 by 1. Right? So think about the pattern that exists in that equation, and think about, I hope maybe after this next one you'll be able to come up with a general rule about when you have certain dimensions, what will the result be. All right, so let's look at this one. So in this one, we've got our a is a 3 by 2, and our x is a 2 by 1. So if we did a times x here, we're going to get 7, 3, 6, minus 2, 1, minus 5. That's our a. We're multiplying by minus 2, 3. Now, this one will work because we've got two columns, A1 and A2, and we've got two entries in the x's, right? X1, X2. And so each one of these columns gets the weights in the vector x. They match up, and so we can do this multiplication. So each one of these scalars gets weights the vector. We add them together. We'd have minus 14 minus 6 is minus 20. Right? Minus 6 plus 3 is minus 3. Minus 12 minus 15 is minus 27. Now again, let's see if we can come up with a pattern here. All right, let's compare the last couple. So we just did ax equals b. Right, and this is our b, just to be clear. That was the outcome. That's our b. And what we did is we multiplied a 3 by 2 times a 2 by 1, and we ended up with a 3 by 1. So maybe take a second, look at what happened in the last couple, and you can also compare it to the one on the last page. Let's just look at that one on the last page quick. All right, so this one here, when we thought about ax equals b on this one, we multiplied a 2 by 2 by a 2 by 1, and we ended up with a 2 by 1. So what's the pattern? Right? How does it work? How'd that one work? How'd this one work? How'd this one work? We actually ended up with the same size thing here, but we had different size matrix and vector, right? So what's the pattern? Well, it says at the top of the next page. Let's flip that over and see that let me write down the general equation. So we're trying to think about when you have a x equals b, how does it work? Right, so when a is m by n, each one of the situations, the matrix X is going to be n by 1. Okay? In other words, the number, what we said previously, is this number, the number of columns of A, has to match this number, which is the number of entries in X. Right? Those have to match. And then in every situation, what we ended up with was a column vector that has this many columns, m columns, right? Like if we put this one back up from the last page, the number of columns in A ended up being, I'm sorry, not the number of columns is what I meant, the number of rows in A. M is the number of rows. Right, so A had 3 rows, and so we ended up with an answer that had 3 rows. Right, in this one, A had 2 rows, and so we ended up with an answer that had 2 rows. And the first one, same thing. A had 2 rows, we ended up with an answer that had 2 rows. And so what we see here is that this number m and this number, which is always going to be a 1, ends up being the size of the matrix B, or excuse me, the vector B. Right? So in the equation ax equals b, the length of x is always going to be n by 1. And then the length of b is always going to be m by 1. And let's, again, go back to the ones we've seen so far and see if that makes sense and checks out. So again, in this first one, this is from the first page, we had ax equals b. These numbers matched up. The 2's matched up. Great. And then this number and this number, 2 and a 1, ended up being the size of the b. Similarly, on the second page, right, this number and this number match up, so that worked. And then 2 by 1 ended up being the size of the answer. And same thing at the bottom here, right? These match up, 2 and 2 match up. That's what lets us be able to do the multiplication. And then the 3 by 1 ends up being the size of the answer. And this is something that's going to carry through once we start multiplying matrices by matrices as well, right? So the inner dimensions have to match up, and then the outer dimensions end up being the size of the answer. And that's exactly what this general form says right here. If you've got an m by n times an n by 1, the inner dimensions match, the answer is going to be the outer dimensions, m by 1. Okay. So let's talk about doing this a little bit quicker. So first of all, you need to have the inner dimensions match, right? If they don't match, you can't do the multiplication. We've sort of said that a couple times, and I just want to be very clear about that. Here's how we can kind of think about doing it a little bit faster. So if we multiply this matrix times this vector, for one thing, we've got a 3 by 3. It's multiplying a 3 by 1. These inner dimensions match, so we're allowed to do it. And that means the outer dimensions, 3 by 1, will be the size of the answer. So just applying what we just learned. But anyway, if we use these weights on those columns, it becomes this, right? It becomes the first column times x1, the second column times x2, and then the third column times x3. And then when we do that scalar multiplication, what we end up doing is this, right? So it ends up being this. Let me write it down and then we'll talk about it. So it ends up being like x1, 2x2, 3x3 in the first spot. The middle row would be 4x1 plus 5x2 plus 6x3. And then the third row is 7x1 plus 8x2 plus 9x3. And this is a 3 by 1, because once you add each one of those things together, it just becomes one entry, right? So this has 3 rows, and then each one of those is just going to be one scalar once you do the addition. But what I'm trying to point out here is notice that, like, the first, what we end up doing here is this x1 ends up multiplying all the things in the first column, right? This x2 multiplies all the things in the second column, and this x3 multiplies all the things in the third column. And so instead of like writing it out like this and sort of thinking about this linear combination, an alternative approach, sort of another shorthand way to kind of think about it, is to take the original, let me just rewrite the matrix A, and you can almost think about the x1, x2, x3, at least this is the way I do it when I think about multiplying. I take this column vector and I sort of put the x1 on the first row, the x2 on the first column, second column, x3 on the third column. And then I think about the x1 is going to multiply all these numbers, the x2 is going to multiply all those numbers, the x3 is going to multiply all those numbers, and then we just add them together. So it's just kind of like we don't have to write out this intermediate step. We can just kind of jump right down to this step, because I know that this x1 is going to multiply each one of those, and you get that, right? The x2 is going to multiply each one of those, and we get the middle column, right? So it's just kind of like a quicker shorthand kind of thing to think about this. Now there are 3 down at the bottom of the page. I usually, stop here and ask folks to think about those in groups. This is definitely your chance to give these a try and think about which ones you can do, which ones you can't do. I'm talking about the ones at the bottom of the page here. Right, there's 3 down here. At least one of them you can't do because the dimensions won't match, so that's your opportunity to think about that. And try it shorthand. I would recommend giving that a try. If you want to see me do another one that is, that's fine, but I really would encourage you to pause the video and at least think about 2 of these. So let me do the first one. So in this particular one, we've got a 3 by 2 matrix, and we're multiplying a 2 by 1 matrix. And so the inner dimensions match up, right? The 2's match up, and so we're allowed to do this multiplication. And the way I'm thinking about doing this, you don't have to write this intermediate step, right? Once you do it once or twice, you just kind of can visualize it in your mind's eye. Right, I think about this taking the 5, 6 and stacking it up here, and then I know that the 5 is going to scale this column, and the 6 is going to scale this column, and then we're just going to add those things together. Right, so this becomes like, I'm going to write the details out here. It's going to be 7 times 5, 3 times 5, minus 4 times 5, right? So we're taking 5 and scaling the first column, and then we're going to add minus 1 times 6. We're going to add 2 times 6. We're going to add 1 times 6. And you can see that this 5, which is the first entry in the x, scales everything in the first column, and then the 6 scales everything in the second column. Again, once you do a couple of these, you can probably just jump right from this to the next thing I'm about to write and just kind of get right down to the answer. As this ends up being 35 minus 6, 15 plus 12, minus 20 plus 6. And so we'll get 29, 27, minus 14. And that's the thing we thought we would get, because our inner dimensions match 2 by 2, and then that means the final answer is going to be a 3 by 1, and that's exactly what ended up happening right here, right? Our final answer was a 3 by 1 column vector, which matched up with the outer dimensions of our multiplication. All right, again, if you haven't tried these, I would at least think about the next couple and what's going to happen on them. On this next one here, what we're doing is we're multiplying a matrix that has 2 rows and 3 columns, so 2 by 3, and we're trying to multiply it by something that's a 2 by 1. And so we don't have to do anything on this one because the inner dimensions don't match, right? The 3 and the 2 don't match. And so this is a does not exist situation. Right? undefined, does not exist, can't do it. If you punch it into a calculator, it would say error, whatever you want to say. You can't do this one. And to think about it a little bit further, if we tried to stack, the scalars on top of the columns like we did in this last one, we basically don't have something to stack on top of the third column, right? So there's A. If I took my 4 and my 5 and put it right there, right, these are going to sort of go through and multiply those. The 5 is going to multiply that column, but there's nothing here to multiply this column, right? So this column doesn't have a scalar to scale it by, and so we can't do this one. Okay, and on tests and quizzes and stuff like that, I do put in things that you can't do. Oftentimes in math, I sort of think of those as like, oh, you're trying to trick me or whatever. But in linear algebra, those situations come up, right? And you need to be able to recognize that you can't multiply things. And so I do want to occasionally test people on that. And you should, if you forget this and you sort of try to do it, you will run into a wall, hopefully, and realize that you can't actually do that one. Okay, on the final one, this is going to lead into the info on the next page, but what we have here is a 3 by 3. We're multiplying a 3 by 1. These inner dimensions match, and so we're allowed to do it, and the answer should be a 3 by 1. And when we sort of rewrite this one doing the stacking thing I just talked about, right, take the 3, 4, 5 and sort of put it on top here. The 3 is going to multiply through the first column, 4 the second column, 5 is going to multiply through the third column. And we just end up with something that's kind of interesting. We end up with 3 plus 0 plus 0, 0 plus 4 plus 0, 0 plus 0 plus 5 when we actually do this multiplication, because there's a lot of zeros in there. In other words, we end up with the exact same thing we started with by multiplying by. Right? We multiplied this strange matrix with 1s in it by 3, 4, 5, and we ended up getting the exact same thing back. And so that's what's called multiplying by the identity matrix. Okay, so this matrix with 1s on the diagonal is called the identity matrix, and that is what is explained on the next page. So I'm just going to flip over and look at that. Okay. So the matrix with all 1s on the diagonal in the previous example is known as the identity matrix, which is oftentimes denoted with a capital I. Or maybe more specifically, I sub n. And n tells us the dimension of that matrix. And so you can kind of think about this as, it's kind of like the matrix version of the number 1 in terms of multiplication. Because when you multiply something by the identity matrix, it stays the same. And that's exactly what this says, right? So given vector x of size n by 1, the corresponding identity matrix of size n by n, denoted I sub n, is such that I sub n times x equals x, right? So you multiply something by the identity matrix, and it stays the same. Notice, too, that the identity matrix is n by n. That means it has to be a square. Right? It has just as many rows as it does columns. And so the identity matrix is always a square matrix, and then the n tells us how many rows and columns it has. And as I mentioned, it's kind of like, in terms of multiplication, it's kind of like the matrix version of the number 1. So for example, if we're in real numbers in matrices that are 3 by 3, the 3 by 3 identity matrix, denoted I sub 3, would be the one we just saw on the last page. Okay, so the characteristics, as we see here, it has 1s on the diagonal and then 0s everywhere else. Okay, if we're in 2 dimensions, so in R2, 2 by 2, the 2 by 2 identity matrix would just be a 2 by 2 version of that, right? Again, 1s on the diagonal, 0s everywhere else. And we can have any size one of these. Let me do one that's a little bit bigger and not get too crazy, but I4 would be the 4x4. Right. Again, it's got ones on the diagonal, right? So that would be the I4 matrix. And sort of one of the key things we're learning about right now is when we multiply I4 times, say, a column vector, 1, 2, 3, 4, right? So this would be a 4x4 times a 4x1. The idea is if we have the identity matrix, we don't really need to think about the answer. It's going to be whatever you're multiplying by. Right? Just like when you multiply by the number 1, you don't think about it. It's just whatever you're multiplying by stays the same. And so in this case, if I multiplied the identity matrix by this 4x1, it's going to just stay the same. Okay? All right, cool. Let's take what we've learned and just create a couple properties or theorems from them. The first one is something that's not super groundbreaking, but I am going to prove it. So I'll do a general proof, which is kind of fun. And this says that if we have an m by n matrix, so not necessarily square, m by n, and u and v are vectors in Rn, then and c is a scalar, then the following are true. So the first one says if you have a matrix times the sum of two vectors, you can distribute the matrix through there and get a times u plus a times v. So you can distribute matrix into sum of vectors. And if you have a matrix multiplied by a scalar times a vector, you can pull the scalar out front, right? So you can rearrange the way, the groupings in which scalars multiply matrices and vectors. As a quick reminder, I should have mentioned this too, the word scalar, that just means it's a real number, right? We saw that definition a bunch of times, but scalar just means some number. Now, I would like to just prove part A for you. You know, we don't do a ton of proofs in this course, but it's nice to see why this is true. Like, how do we know that we can do something like this and it's always going to work? And so here's how you prove something in kind of a general sense here when we think about this. So let me start over. We think about what a times u plus v looks like in general, and then try to rearrange that expression into looking something like au plus av. And if we do it in general, then that means it'll work every single time no matter what a, u, and v are, as long as they satisfy these conditions, right? So what I'm going to do is I'm going to start with the left-hand side of this equation, and I'm going to write out what this looks like, rearrange things, and then eventually make it look like the right-hand side of the equation. And then in doing that, we'll have proved it. So let me write A as a bunch of column vectors, just like we had all throughout this. And then u plus v is going to be some scalars added together, added inside a vector. Right, so we've got the column vectors a1 through an, and then I'm just rewriting u plus v as the sum of two vectors, right? So everything inside here is a scalar. Well, we just learned how to multiply a matrix times a vector, right? Each one of these columns gets scaled by those weights. And so this would become the following expression. Right, so I'm scaling each column of A, and we know they're column vectors, so I've got the vector signs on them, and they're getting scaled by those weights in u plus v. Well, we just have a scalar multiplied by some vectors, and so we can distribute that through there. We learned that in the last section as well. Right, and so this is just going to become a massive linear combination of a whole bunch of different things. And so it'll look like this. So I've just distributed those column vectors through each one of those expressions. And notice too the generality that exists here. I don't know how big these column vectors are. Like, I don't know how many entries there are in them. I got the vector sign on the wrong one there. Sorry. I don't know how big these vectors are, but I'm doing it in such generality that it doesn't matter, right? There's just n entries, and there's going to be n entries in the vector u plus v. And so this applies to any sized matrix and any size vector as long as they satisfy these properties, right? This is very nice. Now what I'm going to do is I eventually want to split apart the A's and the U's and the V's, you can see. So I'm going to group all the U sub i's together and all the V sub i's together. Because right now it's like U's and V's are all, it goes U and V together. So I'm going to group all the A's and then all the V's. So I'm going to rewrite the exact same expression, but I'm just going to group the A's and the U's and the V's. So U1, A2, U2, A3, U3. So here I am grouping the U's. Then I'm going to group the V's. I'm going to do the exact same thing. And then notice that this expression here with the U's is going to be A times U, and this expression here with the V's is going to end up being A times V, right? Because we're scaling the columns of A with the entries of V here, we're scaling the columns of A with the entries of U here. And so let me just write that out a little more carefully. This first part ends up being the columns of A times the vector U. Right? Scaling each one of these columns by those entries is the thing above it. And then the second part, oops, just meant to write A1. Is A times V. Right? And so what we have here really is matrix A times a vector U here. And then we have matrix A times a vector V here. And this is exactly what we are trying to prove. Put a little proof sign there. So just to kind of go back over what we did here, I started out with a general situation of matrix A times U plus V. That's exactly what it looks like here. I did that multiplication, which we learned about in this section. I just rearranged the way things were grouped, right? And then it split up, like this plus sign is this plus sign is this plus sign. And it turned out to be AU plus AV separated separately. And so since this is all generalized, like we don't know how many entries or size of these vectors or anything, this will work no matter what size the A's and the V's and the U's are. And it turns out the proof of B is very, very similar. I'm not going to do that here. But if you follow this one, you can probably follow a very similar process to get part B. Okay. The last thing we'll just sort of apply what we've learned to is the start of a very, very important theorem that's going to carry through the rest of the course. It doesn't have a name right now because we haven't actually learned the word that's in the name. So this is eventually going to turn into something called the invertible matrix theorem. I didn't write that out. I didn't type that out here because we haven't learned what the word invertible means yet. So we're kind of like hiding it a little bit here, but just notice that it has, A, B, C, D parts. By the end of the course here, every section we kind of tack on one or two additional parts to that. And so by the end of the course, these go down through M or N, I think. But let's read through it and see what it says so far. So let A be an m by n matrix, so not necessarily square. Then the following statements are all logically equivalent. What that means is, for some particular matrix A, they're either all true or they're all false. Okay? So this theorem gets applied a lot of the times in lots of future sections, and it shows how all the things we're learning about in linear algebra are intimately connected. So the first thing says, if we have some b in Rm, then the equation ax equals b has a solution. Okay, so that's going to be either true or false. And we learned about that in section 1.4. Right, we know it's going to have a solution if the inner dimensions match between a and x. Well, that also is logically equivalent to every b in Rm being a linear combination of a. So that's just restating the thing we just said a second ago, also from this section. Well, that means that the columns of A might span Rm. We learned about what span means in section 1.3. And then what that means in terms of section 1.2, it means that the matrix A would have a pivot in every row. And so, like this says, these things are either all true or all false. So, for example, if we found out that ax equals b doesn't have a solution, that would mean every other one is also false. That would mean that there's not a linear combination of b that would result from the columns of A. That means that the columns would not span Rm. It would mean that A does not have a pivot in every row. Right? Flip side of that is, if we learn that A has a pivot in every row, that means that the columns do span Rm. That means that there is some b that's a linear combination of the columns of A. Right? So they're either all true or all false. And the way that this is often applied is you learn some information that tells you whether one of them's true, and then the question asks you about one of the other ones. Okay, so this is just to kind of drive that home. This is a very important theorem. We're going to keep adding to it, and it's particularly important for two homework questions that I'm going to write down in just 1 second. This is a very important theorem that we will continue to add to in most future sections. And in particular, it gets used on a lot of homework questions. And in particular, in 1.4, the first opportunity you'll have to use this is on homework 1.4, numbers 17 and 19. Okay, so when 17 and 19 come up in 1.4, flip back here, you'll be able to tell whether one of those things is true or false, and then it means that all of them are true or false. Okay, I'm happy to talk about that during our meetings.